Okay, so the third question is from exam 3. Here we're going to work with pedigrees and ratios or probability. So looking at pedigree A, what I usually try to do is figure out whether it's dominant or recessive. Sometimes looking at one segment helps. So if I look at this segment in pedigree A, I can see that both parents are affected and they give rise to kids that are non-affected. So I can assume that they're heterozygote for the trait, and so the dominant trait is the one that has the disease, and then they have the recessive trait does not carry the disease, and it came out in their kids later on. So this is definitely dominant. Can do the same thing for pedigree B, but same and opposite in a way. So look at the ones I'm going to highlight here. In this case, the parents don't have the disease, but they have kids that might or might not have the disease, which also means that those parents are heterozygote. The disease is recessive, and that's why they don't show it, but then half of their kids might have it, something like that. Not that it's the probability is half, I'm just saying some of the kids have it, the other some doesn't. So it's recessive. Okay, and we discussed dominant and recessive in an earlier video. So I figured out whether it's dominant or recessive. Now I want to figure out whether it's autosomal or X-linked. In pedigree A here, so now that I know it's dominant, if it's dominant and X-linked, the father has it, he will only give X to his daughters, right? So, but in this case we see that the son has it, so that means it's not X-linked, so it's definitely autosomal. Apologize for the way it came out. Anyways, and now looking at pedigree B, if I choose a random segment, this is one of the segments I highlighted earlier. Again, the father will only give it to the daughter, right? Because he gives the X to the daughter, and the mom will give the X to the sons, right? Since we have an affected daughter and the father is not affected, that means she didn't get an affected X from dad, and she needs an affected X from mom, and if mom is a carrier, she won't show it because we already figured out it's recessive. It cannot be X-linked. It's definitely autosomal. The thing is, the first clue is when you see an even cut or number effectiveness between males and females in the whole pedigree, it tells you it's autosomal, but you have to check that out using a small segment of the pedigree, and when I did the checking I found out that it's autosomal, so it just confirms with the general overview when I look at the pedigree and I see most of the males and females are affected. But again, you have to check a small segment and confirm your conclusion. So we figured out whether it's autosomal or X-linked, whether it's dominant or recessive, and we got the answers. Part C of the question asks you what's the probability that a child between the underlined people in pedigree A will have the trait. So let's look at pedigree A. These are the people involved. Oh, and before I even answer that question, let's go with convention. So for pedigree A, since I know it's dominant, the trait is dominant, capital A is, this is capital, means it's dominant, and it's for someone that has the trait. Small a is no trait or normal. Here, since I said it's recessive, so you need 2 copies of lowercase b to have the trait. And then capital B is no trait or normal. Okay, so here are our conventions. Now going back to pedigree A, since the father here does not have it. I know that his genotype is small a, or lowercase a's. The mother here, she, looking at her parents, let me write the cross, so cross with the mother. Looking at her parents, her dad had it, and so he gave a copy to his daughter, and her mom had both lowercase a's, and she gave that copy to her daughter. So I know that her genotype looks like this. So I have het times homozygote, so it's 1/2. So that's how we found that out. And now part D, they're asking you what is the probability that the child, between underlined people here and here, will have the trait. Okay, so for the dad, it's easy to tell that he has 2 lowercase b's, and he has the trait. The mother, on the other hand, I want to figure out her genotype because she can have 2 different genotypes. Before I go into that, let's look at her parents. So her mom has capital B small v, her dad has capital B small b. They're both heterozygote, that's why the kids, her siblings, came out, some of them having the trait, some of them don't, and including herself. And so if I have het and het, the ratios that I know of is 3:1, and the mother, the one I'm looking at, falls in the 3 category, so I don't care about the 1 category. And then the genotypic ratio is 1:2:1. So 1 again represents someone that has the trait, and the mother does not have the trait. But she can be a carrier for it. Okay, or she can be homozygote for the normal trait. Okay, the probability of her being a carrier is 2/3. The probability of her being homozygote is 1/3. So here, when I want to cross the father with either mothers, like the probability for the mother, either probabilities for the mother, it's going to be 1/3 of her being homozygote for the trait, or 2/3 of her being carrier for the trait. So when she is homozygote for the trait, it's 1/3 times homozygote times homozygote. It's 0 probability of the kid having the trait. Again, it depends on whether you know your ratios or not. That's how you're going to figure it out. You can draw a Punnett square, and then or represent positive or an addition. 2/3 times, since the mother here is heterozygote and the father is homozygote, so the probability is 1/2. So the answer is 1/3. So we figured out the answer for their kid having the trait. Then part E, they're asking you what's the probability that all 4 children in the dotted region will be carriers for the trait. So here's our dotted region over here, and if all of them have the trait, that means that child number 1, 2, 3, and 4 are carriers for the trait. That means 1 and when we say and, it means we multiply child number 1 multiplied by child number 2 and child number 3 and child number 4, all of them being carrier at the same time. So, and the probability for each child is the same. So the probability for this child is the same as the probability for this child, this child, this child, but we're going to multiply it. So what I need to do right now is just figure out the probability for one of them, which is going to be the same for the rest because we want them to be carriers. So we look at their parents. First step is, if I look at the father again, so the father, okay, let's look at the father's parents. His dad has both traits. His mom is a carrier for the trait which explains why some of his siblings have the trait. It just means that he got uppercase B from his mom and then the lowercase from his dad, so I definitely know his genotype. The mother, though, on the other hand, if I look at her parents are heterozygote for the trait, both of them, because both of them look normal, but then when the trait appeared in her brother, which means the brother got a small b from mom and a small b from dad, so that's why they're heterozygote for the trait. And so we did the calculations earlier. The daughter has 1/3 chance of being homozygote for the normal trait, or 2/3 probability of being a carrier. Okay, so that means when we cross the father with the mother, oops, it just happened, with the mother, the probability of her being carrier or not is 1/3 BB. Just one sec.
Shoot at 3:45.
Apologize for that. It just means I have to leave the room I'm in soon. Anyways, so as I was saying, it's 1/3 probability of her being homozygote plus, because it's or her having the other genotype, 2/3 of her being a carrier. Okay, so het times homozygote is 1/2, right? So 1/3 times 1/2 plus heterozygote times heterozygote is 1/4, right? So 2/3 times it's 2/4 for being carrier. So it's 2/4. So if I was to simplify this, I'll have 1/6 plus 1/3, which is equal to 3/6, which is equal to 1/2. Okay, that's the probability for one child, and I said I have 4 kids, so it's 1/2 for the first kid and the second kid having it, so I multiply, and the third kid having it, so I multiply, and the fourth kid having it, so I multiply. It's 1/2 to the power 4, or in other words, it's 1/16. And that's the probability of all kids being carriers, and that's how you find it. Thank you.